morning, everybody. Welcome you all again to this course. Actually, we have provided you the class schedule. This was prepared in consultation with Professor Giovanni as well as my other engagement in the department. So today, every day there is tutorial. We have designed the course in such a way that every day you will get 2 hours tutorial, laboratory or some module in software in computer like that. And as well as there is 10-hour lecture and 10 hours practical. We have thought of, it is mentioned, in our institute we have a nice facility for geological museum, and it is one of the best of its kind in India. Nowhere in any academic institute you will find a geological museum, and Department of Applied Geology have agreed to accommodate all our participants and to explain all different kind of rock mineral they have in their collection, and we will visit on Wednesday afternoon. That will be mentioned at 4:30. Another facility in our department, it is also unique in that nature. We have a artificial longwall gallery. Means it is a underground coal mining extraction procedure, method of extraction. We have a real longwall facility, all machineries and transportation in the surface itself. We will also visit that place in the last day on Friday. Okay. So that is already, the rest of the topic is already mentioned, particularly in the topic as well as the title. We have thought of providing, we have not given you the hard days pen drive. In that pen drive you will get all the volumes to be delivered in this course. So don't worry, you will get the pen drive shortly, because we are on the process of compiling everything. Probably 1 or 2 days we will get it. Okay. And this course have a nature that we need to test ourselves, not you, that how much we have delivered. So that is why we will take a formal class test. Okay. So that test, as we have planned, discussing with Professor Vasily, that it would be 1 hour. Total marks would be 50. Okay, 50 marks, 1 hour. Okay. And in that later, after the course is finished, we will intimate you the mark sheet. In that, at the end, we will get the certificate, participation certificate, but we will take some time to evaluate the papers. Then we will intimate you individually the mark sheet of the course that is required for the MHRD GIAN guideline. And at the end, you have to visit again in the website, each and every personal portal to give the feedback. I will get back to you again in the day before the last class. Okay. So this is all. So now I request Professor Vasily to come over and take the class.
So, dear Vic, I hope really you can hear me, and I know that I have a quite thick English accent in my Italian, so I hope you can understand that. So, and if you don't understand, I'm trying to speak slowly. If you don't understand, ask. But this is my accent, and I hope you get a little bit used quicker than later, sooner than later. So now the idea of the course is really to give you an introduction to rock mechanics. But what is called there is written in the title, and that was the idea, is that modern advances. So, and what I feel that when you look at these books, this is actually geological engineering, rock mechanics, all those books are actually dated the last millennium. So, rock mechanics is really, it's a new subject, was sort of developed after a number of disasters, specifically mainly related to dam stability. Malpasset Dam was one dam in France that really collapsed, and the collapse was related to the failure along a joint that was underneath the foundation of the side of the dam. And the other big disaster that actually gave a push to the creation of rock mechanics was the rock slide that led into the artificial lake in Italy, the Vajont, and that created a huge tsunami that overtopped the dam and wiped completely the valley, and several thousand people died in that event. Well, everything you can see as a bad event, but it was also a success of engineering, if you wish, because the dam was intact. So it's just you can always try to see some positive aspects even in these tragedies. So no matter what, after that there was the number of people that start looking at paying more attention not just to the soil but also to the rock. And rock mechanics was pretty much born in the 60s. So, and a lot of work happened from there till probably the 80s, and that was translated into books. But what I feel is that those books have actually been frozen in time, and that is still what probably you're still learning in the textbook that you can buy or find in the libraries. So I've been very debated in what I'm going to present, and I was not really sure what was the crowd. The crowd is mainly undergrad. So what I'm going to give you is actually my particular vision of the rock mechanics. I've tried to give you the basics, so coming from the 60s, 70s, maybe earlier as well. But then what I would say, I want really you to start thinking about we are in the almost 2020, it's not many months that we're going to get there, and technology is completely different with respect to the 60s. So how we can look at these the rock mechanics with really a modern view. So and there's a lot of things I would like to, you're not finding in these books. And a lot of things that start appearing, and the new generation of rock mechanicists are actually more and more embraced. So that would be, to me, is a challenge. What I would like you to leave is with very few concepts. I would say common sense, the engineering common sense that will definitely serve you wherever you're going to work in tunneling for subways, in mining, in slope stabilities, in open pit, underground, whatever you are going to actually work. But at the same time, what I would like is also you to be aware of what we are doing from a scientific point of view, what are the tools that you might actually start using already now that I think could really easily and better replace what has been done so far. Okay, so that is pretty much what as my introduction. So, and it's getting warm. I'm used to have jacket down there. So okay, now the other thing is that you are going to get all these slides plus papers that have been published recently that sort of summarize or review the particular topic and will bring a little bit more up-to-date information with respect to the text. So what you're going to get is really the compilation of the slides that I hope will be serving you, but also the papers where you can find many more detailed information. So the first thing that we need to go through though is no matter, most of you are actually, you're all engineers, so I'm sure that you did solid mechanics, so you should be quite good in stress and strains. So, but I remember that every time I look at these slides, I say, oh yes, I'm trying to remember, because you look at them, you use, and you forget. So that's pretty much what we are going to do. So I need to get used a little bit of what I'm using. So that's the first lecture. and I'm going to fly with this. But really, what I see this is a sort of a refreshment of what you should already know. And again, all what is there will be given to you. So the equations, well, and all the others will be available. So just a couple of things, just a definition. Just let's remind what stress is and what strain is. So stress is basically a force that is applied over an area. And stresses can be compressive stress, can be tensile stresses, can be shear stresses. So it depends really how they are applied with respect to that particular plane where the force is going to be distributed. The strain is really the result of what the action of the forces in the body. So it's really the deformation. So that means is how shortened or what is the elongation of that body with respect to its initial dimension. That's pretty much what you need to remember. So what we are looking at is, well, the force really is a vector. You can always resolve your vector in, for example, a normal and a tangential component with respect to a point, a plane. And the stress is really the distribution of that particular force with respect to an area. So it's really defined with respect to a plane. And that's really what we are going to use. So the stress is at the end is a property at a given point. And within a rock mass, what we are looking and trying to always understand is what is the stress at one given location. Because that stress will result in a displacement, in a deformation, and that deformation is really what is going to cause potentially the failure of your rock. And that is really the challenge. And what I really would like is there's math behind. I don't really like to. I mean, math is a very nice tool, but shouldn't be the goal of this course. It should be a tool. So it's a tool to actually understand and resolve mathematically what is the condition of the rock. Okay. So the thing that we need to remember is, and that is very important, that stresses with respect to the plane can be perpendicular, so normal stress, or can be sort of tangential to that plane, and those are the shear stresses. And those are the two things that really we need to care, because those are the stresses we need to resolve, and we need to understand to really figure out if our rock is going to be stable or not. That's pretty much what we have. So from a mathematical point of view, yes, we can have our cubic element, and then we can resolve stresses in the three axes. Those are sigma x, y, and z, and on each single plane, single facet of that cube, we can resolve basically along those two axes that we arbitrarily choose what are the shear stresses along those facets. So, and mathematically, we can write them in matrix form. Then, what we can is that because of the equilibrium, we can actually derive that that matrix is symmetrical. So, for example, tau xy is equal to tau yx. Okay, that's something that I'm sure you have already done, right? Yes. I'm not asking if you remember. I'm asking if you have done it. Yes. Okay. That's a very big difference. So, and I know that you have the notes, and if you need, you will go and try to find them, or maybe Google for the solutions. That's fine. So, the other thing is actually important is that we can always find the directions along which the shear stresses basically disappears and goes zero. So, our matrix becomes diagonal mathematically. But that's important because we can actually define our stress state with only three variables that are called principal stresses. and generalize sigma 1, sigma 2, and sigma 3, where 1 is the highest, 2 is the intermediate, and 3 is the medium. And those are the three stresses that we are always looking at. But we need also to know how to go from one state, one orientation of our small cube, where we have only sigma 1, sigma 2, sigma 3, to another one where we have also the shear components. Why do we need that? Any idea? Why do we need that? Oh, by the way, I'm asking questions, and I was told that normally these type of classes you are extremely talkative. So just don't tell me that it's not correct. Why do I care? Why do I care to know, to be able to go from one orientation to the other? What do I care? Okay, I will ask you later. You don't want to answer? Okay, you will get the question again. So the other thing is that, oh, sure, that's the answer. So why? Because we can always resolve what is the normal and the tangential force on any given plane. Specifically on a plane, for example, where a fracture exists. So we know what is the shear force on that particular plane and the normal force on that particular plane. And one very simple way to actually picture that in two dimensions is nothing else than using the Morse series. And you will remember. It's good. So the other thing that is important is that to realize that when we apply stress to any body, that body will react in some way and will start to deform. So, and that means that there will be that deformation that is related and associated to the stress that is applied. Right? So if the material is perfectly elastic, the ratio is so-called E, that is the Young modulus. Okay? And that is what our books are saying. We can find the Young modulus of rock, and we're happy because we can design anything with that. And I will see what is the flow then. So, but that's correct that normally when you have a linear relationship between the strain that you measure and the stress you apply, that is really the elastic behavior of the material, and that relationship can be described by this quantity that is E. That is nothing else than the slope of the plot in between the strain and the stress applied. Okay? The other thing that we need to be aware is that when I deform a material, so I apply, let's say, my force along one single axis, what is happening is that, yes, I make that object shorter. So I do that. Oh, it became shorter. But at the same time, what is happening is that the material does that. Right? It also deforms on the other two directions. So what we can define is another quantity that has been defined called the Poisson ratio. That is actually the ratio in between the lateral strain and the axial strain. Right? So if we have a cube, we can define actually two different lateral strains, one along, in this case, Z, and one along Y. Right? So we have two Poisson ratios. If it is linear elastic, those two Poisson ratios will be exactly the same. Poisson ratio is a constant for a material when it is a linear elastic material. Okay? the other thing we can do is also put all together all those informations. So the strain, stresses, and they can be related by quantities such as Poisson ratio. And those relationships are going to give us really what is the constitutive law of the material. Okay? And the constitutive law of the material is nothing else than telling us how the material deforms under a particular given stress. Okay? And that matrix in the middle is really made of those elastic constants that basically are the Poisson ratio and the GIAN. Okay? Now, I just spoil you immediately all what I'm going to say. This is valid for linear elastic or elastic material. Is the rock elastic? That's the question. And the answer is no. And that's the problem. Or, well, no. It is in a very specific range that personally we don't care. Because what we are looking at is always to avoid the failure, but to get as close as possible to the failure as we can. And when we get there, well, the material is not elastic anymore. So that's a challenge that we faced, especially in mining. Okay? So that's pretty much what we're doing. Now, the thing that we need to always to be able is really to resolve the stress in any direction. Okay? So, specifically, what we want is, given a particular stress state, and generally what we like to use are the principal stresses where the shear disappears. But then we have fractures, we have features, geological contacts, or whatever you want, where actually we need to know what is the shear stress that is applied there, and also the normal stress, because the two will tell us if the particular conditions of stress and geometrical condition is going to be stable or not. That's really the challenge. So we need to be able to resolve what are the normal stresses and the shear stresses on one given plate. And that is where the math comes back. So at the end, what you want, you basically want to transform your stress tensor, and you want to resolve what is the condition of the stress in that particular direction. Oops. So basically, you start using this as equations. You remember that, those, right? Do you? Yes? Solved out, you said? So far and so far. So my point is that, yes, you have this math and you actually need to use it, because what we want is really be able to go from one condition to the other and back. So if you do this calculation all the time, you will remember by mind this. They're going to be your friend. The reality is that if you don't do this calculation all the time, and you have a book, and you'll be having these notes, and you can refer to them and just use them. So, and then what you can is also to calculate what is exactly the orientation, so the angle with respect to which you need to orient, turn your particular stresses. And this actually is very important, because it's going to tell you what is the orientation of the principal stresses, and those are going to tell you how the rock is going to behave. And that condition is really what you need to understand, so more than the math behind, that I'm sure that you can solve those equations. What I really would like is to start to understand where and how those stresses will be oriented, where the principal stresses are going to act with respect to a particular condition. A little bit more equations, a little bit more equations. I know, I'm skipping that because I'm not going through those math that you can solve by yourself. Or either analytical or just using the more circles. Okay? And there's a particular condition that is pure shear. But what I think is much more interesting is this one. And this is really what we should start looking at. So we should start thinking about how the stresses are going to be distributed with respect to the rock, and start understanding on how the rock will respond under those stresses. Okay? Right? So the exact value of the stress, yes, you can calculate. But as an engineer, especially in the mine or in the tunnel, a rock mechanics engineer, you need to be able to have a guess and understand how the rock might respond and what are the stresses that you need to deal with, even before calculating. That comes from experience and comes from actually understanding of the physics behind, right? And that is really, I think, what makes someone good in solving equations to a good engineer. You need really to understand how the rock will behave. Then you do the calculation just to verify and to have really a number, a value, or a range of values. Because you have so many uncertainties in rocks that you cannot really have just one single value. You need to have a range. That range will help you to actually engineer your problem and solve it. Okay? So now, who's doing civil? Most of you, right? That's good. So what are the principal stresses of this model? What is sigma 1? Any idea? Come on. You're saying. What does it mean? What are the principal stresses? Can you give me the orientation? At least the orientation. I don't care about right now the magnitude. But you can tell me what are the relative magnitudes, and you should be able to give me the directions. What vertical? I'm looking at the direction of sigma 1, sigma 2, and sigma 3. And actually, you can give me even the magnitude, at least of one of those. And you speak loud, because I'm trying to speak loud, you need to speak loud. If I don't hear you, I cannot.
Weight of that beam. Weight of this beam.
Okay?
It's vertical.
Okay, it's vertical. That is a weight. Okay, I'm asking the sigma 1, sigma 2, sigma 3.
Becomes sigma 1.
So what is the definition of sigma 1, sigma 2, sigma 3? Is the shear equal to 0, right?
Yes.
Okay. Can you find where, do you know anything about shear equal to 0 here?
So symmetrical. That's why the only shears from sway only.
I'm not sure I understood what you're saying, but
Actually,
yeah, come in. Yeah, come. Hey, it's easy.
be.
I'm looking at this one. You want to do that? That's fine. We can do it.
No, actually.
Let's go with this one. It's easier.
There will be this way. Yeah. Shear force will be 0 over here.
So here is 0.
I mean, for this column it will be 0.
Yes. So
principal stress means it's like shear stress will be 0.
right.
So I think this is a symmetrical one and there won't be shear. So this can be a stress. Principal stress, vertical stress.
Okay. One is vertical. Okay.
Okay, that's the weight of
Yeah.
this.
The weight is okay. That's a vertical one. It's a sigma 1, sigma 2, sigma 3.
Sigma 1.
Sigma 1 vertical. That's okay. Do you agree? Are you following what she's saying? She's good. She's very good. She thank you. That's good. So what is sigma 3?
I'm not sure.
So so she was right. She started thinking, is there any shear stress on this plane? No. So definitely this plane as perpendicular to this plane is one of the maximum the principal stresses, right? Is there any force acting besides the air pressure? No. So basically you can assume that this actually is a 0. So very likely this would be what I would say is a sigma 3, is a 0. It's a free surface, so if you disregard the atmospheric pressure, that's 0. So that would be your sigma 3. Because of the structure, very likely sigma 1 will be vertical and the sigma 2 will be horizontal. Okay? Right? So, but just thinking about that, you can, I'm not going to, I was thinking about just drawing on. So what you can is immediately give an orientation of your stresses, and that will help you in really framing the problem in a mathematical way. And already just by looking and observing that this is a free surface with no shear component acting on that, that would be your one of the 3 principal stresses that are orthogonal. So you know that 1 would be orthogonal, would be equal to 0 in this case, right? Very good. So, and that is pretty much what you need to start thinking about. Start thinking about where the principal stresses are oriented with respect to your geometry by simply looking at what is the definition, 0 shear stress on that particular plane. Right? So, and when you start doing that, you bring a lot of common sense in the calculations, and you can actually connect what is the math behind and the reality. And that's what you need to be able to do. Okay? What does it mean? It means that, let's go back to the fact that unfortunately our rocks are not nice material. A geological material has been created very long time ago and went through a lot of stresses that has really broken that rock. It means that there are fractures, right? And fracture is something that is pretty much open. Okay? So you can think about that is a free surface, right? So when you have a fracture that is open, what can you tell me about the stress acting on that surface? If it is fully open, then detach, how the principal stresses are oriented. So there is an air gap there. What are the stresses acting at that point? It's not touching. Sigma 1? Sigma 1. Yes. How much is sigma 3? Would be 0. So, right? So, if it is sigma 3, I know that my sigma 1 is always perpendicular. So, my sigma 1 would be perpendicular, or 2 by sigma 3. So, it means that sigma 1 will be parallel to that particular fraction. So, what does it mean? That I have my cube, or my sort of in situ stress, with a sigma 1, right, I decide to be vertical, sigma 3 horizontal. What it means is that here is sigma 3 disappears, sigma 1 is sort of oriented with respect to the direction of the fraction. Right? So what it means is that you have stress state in A, far away, your far field stress. And the closer you get to the fracture, that stress is disturbed. It means that it's bothered by that fracture, and my principal stress will start rotating up to basically becoming a sigma 1 parallel to the fracture at the surface of the fraction. Okay. Do you understand that? You don't understand. What do you understand? What do you don't understand? Why? So what you have that your stresses that are applied to your rock mass far away, that they feel the presence of your fraction. And that presence of the fraction, because it is open, means that at the surface of that fraction, I will have a 0 sigma. So the only stress that rock at the surface will feel is really parallel to your fractures. Okay? But here was in that oriented that way. There would be oriented this way. Means that your stress goes from, let's say, sigma 1 vertical to sigma 1 parallel to the fraction. And means that it will start rotating up to there. Plus, the magnitude is going to change. Because you need to remember that the first invariant of the stress says that basically the sigma 1 plus sigma 2 plus sigma 3 is a constant. So in this case, I disregard by sigma 2. Sigma 1 plus sigma 3 must be constant. That means that what is happening is that from a state of stress in A, C will experience basically a 0 sigma 3, so sigma 1 becomes much higher. What does it mean? It means that the rock will be subjected to a much higher stress that could be getting closer and closer to the point where the rock can fail. Right? It's okay? It's okay? Sometimes I don't understand when you do that, it means yes. To me, this is yes, this is no. So I'm getting a little confused. But that's the point. So that leads to another point. The fact that if you're creating an opening in the rock, could be a fracture, could be an excavation, could be whatever is an empty space, the empty space will perturb your stress. Means that your stress will change locally. The direction of your principal stresses will change. And the magnitude of the stresses will change. Yes?
So is it necessary that the principal stress will be parallel to that friction?
The principal stress, the maximum principal stress will be parallel to a free surface. If the fracture is a free surface, yes, it will be parallel. Okay? If the fracture is fully open. If it is not fully open, well, things become a little bit more complicated. Okay? Are you okay so far? Confused? Are you? No. Oh, I thought yes. That's good. You're not. I'm doing a good job. So. Or you came already prepared. Now let's get on this trouble block. Now let's look at fracture. Now that fracture is filled. Okay? And we have 3 cases, case 1, 2, and 3. Okay? So the first case is an open discontinuity. It's exactly what we saw before. So we have our stress cube and is oriented with my sigma 2 and sigma 1. Sigma 1 is horizontal, sigma 2 is vertical. Okay? And I have this fraction, this discontinuity. It's open. So case 1 means that at this particular point, my sigma 3 is 0, and my sigma 1 will be oriented parallel to the open surface. Is the pillar, same concept, okay? So it means that your sigma 1 will rotate in this way. So okay? Do you follow that? Is okay? That's easy one. Now, let's say that the discontinuity is filled with the same material as the rock. So basically what does it mean? The discontinuity pretty much does not exist. Okay? So in that case, what we have is that my block, my stress block, will never change. There's nothing that will perturb that, right? It's fine. It's okay? There's another case where we might have an infilling, so my fracture is filled by a much stiffer material. So let's go back. Is the air stiffer or softer than a rock? Softer, right? So means that case 1 says that your Young modulus of the infilling air in this case is much smaller than the rock. So in that case, what happens is that sigma 1 will orient parallel to that discontinuity. If the infilling is the same as the rock, doesn't matter. Nothing happens. So the stress will keep being oriented as in an intact material. Okay? If you have a much stronger, a much stiffer material, what happens is that, what does it happen? It happens that actually, in the blue, what you have, your material, your stress, will start to orient exactly the opposite. So it means that your sigma 1 will not be parallel anymore to the discontinuity, but will be perpendicular to that particular feature. Okay? So what we're getting is that depending on what is the, see if there is a contrast in stiffness in your rock, that contrast in stiffness will perturb the orientation of your stress state. So your stress will feel the stiffness of the material. Okay? And will be rotated. And that is really what you need to understand where you have to deal with a rock mass that is not homogeneous but is heterogeneous. Means that the stiffness of that material will be different from location to location. Okay? And this actually is very important in mining because when we have intrusions like dikes, those dikes will basically highly influence the stress, will completely change the stress state with respect to that particular feature, geological feature, and will create problem in the sense that a highly concentrated potentially stresses. Okay? Oh, I have an hour left. Do you have questions? So what I really would like is, what I'm trying is to bring a little bit of common sense into the math that is behind a stress state. That's pretty much what I think you need to start, what you should be able to do. Calculation, I trust you can do that. There's a lot of numerical tools that you can use. But understanding how to interpret the numerical tools and understanding if they make sense, the results that you are obtaining, not just green and red colors, that's important. That's really the value that you, as engineers, will bring through the modeling. It's not just a nice red and blue plot, or green, or whatever you want to use as a color scale, but it's really the interpretation, what you translate those to real cases, and especially you need to be able to understand if those plots make sense or not. Okay? And that is really the added value and the reason why you will be eyed by whoever is going to commission that particular study. Now, say that this is really the basic. Now let's see a little bit more about load and failures. So what we said is that we have a force that is applied to a block of rock. That force is distributed across some sort of a plane, a surface, and you have a stress that is defined as the force divided by the area. You create a displacement, then a deformation, that's